Hello. You're drifting with Science Blanket, your quiet space for late-night wonder. Tonight, we're wrapping ourselves in the gentle science of how the weather works. Instead of storms or wind, think of the atmosphere as the earth breathing, a slow, global dance of rising warmth and falling mist that constantly seeks a state of perfect balance. As we begin, imagine yourself floating among clouds that drift like thin ribbons of silk. You don't need to predict the rain or understand the pressure systems. Just let the steady rhythm of the sky tuck you in. If this blanket of knowledge helps you find rest, please subscribe to help other sleepy souls find their way here. Now, take a slow, deep breath. Let your mattress take all your weight, softening your shoulders and letting your eyes grow heavy. Give yourself permission to let the day fade away. Let's explore the quiet wonders of the weather together. The weather that surrounds us, that touches our skin and moves through the trees, happens in a surprisingly thin layer of air. This layer, called the troposphere, extends only about 7 to 12 miles above the surface of our planet, depending on where you stand. It's the lowest layer of Earth's atmosphere, and within this relatively narrow band of gases, all the drama of weather unfolds. The clouds that drift across the sky, the winds that carry leaves down autumn streets, the rain that taps against windows in the night, all of it takes place in this shallow envelope of air pressed against the Earth's surface. Above the troposphere, the air grows thin and still, but here, close to the ground where we live our lives, the atmosphere is alive with constant motion and change. This motion, this endless circulation of air and moisture, doesn't happen by accident or chance. There's an engine that drives it all, a vast and ancient power source that has been fueling weather for as long as our planet has had an atmosphere. That engine is the sun. Solar radiation streams across the emptiness of space, traveling 93 million miles to reach our world, and when that energy arrives, it sets everything in motion. The warmth you feel on your face on a sunny afternoon is the same force that spins hurricanes into existence and lifts water from the oceans into the sky. Every breath of wind, every drop of rain, every snowflake that has ever fallen traces its origin back to the light and heat radiating from our star. The sun doesn't just illuminate our days, it actively creates the weather itself, pouring energy into the atmosphere and setting the stage for all the patterns and processes that follow. But the sun doesn't heat our planet evenly, and this unevenness is absolutely crucial to understanding why weather behaves the way it does. The angle at which sunlight strikes the Earth changes depending on where you are. Near the equator, in the tropics, the sun climbs high overhead, and its rays strike the ground almost directly. This concentrated beam of energy delivers intense heating to these regions, day after day, year after year. Meanwhile, toward the poles, the sun never rises very high in the sky. Its light arrives at a shallow angle, spreading the same amount of energy over a much larger area, like butter scraped thin across toast. The poles receive far less heating than the tropics, and this creates a fundamental imbalance, a difference in temperature between different parts of the planet that nature constantly tries to resolve. The atmosphere and oceans work endlessly to transport heat from the warm equatorial regions toward the colder poles, and weather is essentially the visible expression of this heat transport in action. This differential solar heating, this uneven warming of our planet, creates patterns of air pressure that wrap around the globe in distinct belts. Where air is heated strongly, it rises and creates areas of lower pressure. Where air cools, it sinks and creates higher pressure. These pressure belts don't sit still. They actively drive the movement of air from place to place, generating the great wind systems that encircle the Earth. The trade winds that sailors have relied upon for centuries, the westerlies that push weather systems across the middle latitudes, all of these persistent winds arise from the global arrangement of pressure differences created by the sun's unequal heating. The atmosphere organizes itself into a pattern, a structure that remains remarkably consistent even as individual storms and weather systems come and go. But there's a twist to this story, a complication that makes weather more interesting and complex than it would otherwise be. The Earth doesn't sit still beneath the moving air. It rotates, spinning once every 24 hours, and this rotation has a profound effect on anything that tries to move across the surface, including air. This effect is called the Coriolis effect, named after a French mathematician who described it in the 19th century. The Coriolis effect isn't a force exactly. It's more like an apparent deflection that occurs because we're observing motion from a rotating frame of reference. Imagine standing on a spinning carousel and trying to throw a ball straight to someone standing across from you. From your perspective, the ball seems to curve away in a strange arc, even though you threw it straight. The Earth's rotation does something similar to moving air, bending its path in ways that would seem impossible on a stationary planet. This deflection has consequences that ripple through every aspect of weather. Winds don't simply blow straight from areas of high pressure toward areas of low pressure, as you might expect. Instead, they curve. In the northern hemisphere, the Coriolis effect deflects moving air to the right of its intended path. In the southern hemisphere, the deflection goes to the left. This means that wind systems spiral rather than simply rushing inward or outward. Low-pressure systems spin counterclockwise in the north and clockwise in the south. High-pressure systems rotate in the opposite directions. The Coriolis effect shapes the circulation patterns of everything from dust devils to hurricanes, and without it, the weather on our planet would be utterly different, far simpler and far less interesting than what we actually experience. In the middle latitudes, roughly between 30 and 60 degrees north and south of the equator, a particular pattern of circulation dominates the atmospheric flow. These are called Ferrel cells, named after William Ferrel, an American meteorologist who described them in the mid-1800s. In these regions, the atmosphere doesn't follow a simple rising and sinking pattern. Instead, air gets caught up in a more complex circulation, driven partly by the tropical cells to the south and the polar cells to the north. The Ferrel cells transport warmth poleward, carrying heat away from the tropics and helping to moderate temperatures in the temperate zones where many of the world's population lives. The prevailing winds in these cells blow from west to east, the famous westerlies that dominate weather patterns across much of North America, Europe, and the southern oceans. These westerly winds push storm systems along, creating the changeable, sometimes unpredictable weather that characterizes these latitudes. Closer to the equator, a different circulation pattern prevails. Here, intense solar heating causes air to rise vigorously, creating an updraft that reaches high into the atmosphere. This rising air spreads outward at high altitude, moving toward the poles, and eventually sinks back down around 30 degrees latitude in both hemispheres. This circulation, from equator to subtropics and back again, creates what we call Hadley cells, named after George Hadley, who proposed the mechanism in the 1730s. The Hadley cells are responsible for the trade winds, those steady breezes that blow from east to west across the tropical oceans. As air sinks in the subtropics, it creates regions of high pressure and generally clear skies, the latitudes where many of the world's great deserts are found. As it returns toward the equator at low altitude, the Coriolis effect curves its path, creating the northeasterly trade winds in the northern hemisphere and the southeasterly trades in the south. These winds were the highways of sailing ships for centuries, reliable and persistent, driven by the simple but powerful circulation of the Hadley cells. At the highest latitudes, near the poles themselves, yet another circulation pattern completes the global picture. Polar cells are simpler and smaller than their tropical and mid-latitude counterparts. Cold, dense air at the poles sinks and spreads outward toward lower latitudes. As this frigid air moves equatorward, it's deflected by the Coriolis effect, creating the polar easterlies, winds that blow from east to west in the highest latitudes. The polar cells are the weakest of the three major circulation cells, but they play an important role in moving the coldest air away from the poles and maintaining the temperature gradient that drives so much of the global weather machine. The boundary between the polar cell and the feral cell creates a zone of sharp temperature contrast, and along this boundary, storms frequently develop, drawing energy from the temperature difference and creating the weather systems that bring rain, snow, and wind to the higher latitudes. These great circulation cells don't remain fixed in place throughout the year. They breathe and shift with the seasons, responding to changes in solar heating as Earth tilts on its axis and orbits the Sun. One of the most dramatic consequences of this seasonal shifting involves the subtropical high-pressure zones, those belts of sinking air created by the Hadley cells around 30 degrees latitude. In summer, as the Sun's most direct rays migrate north or south of the equator, these high-pressure belts shift with them. This seasonal movement is crucial for understanding monsoons, those dramatic reversals of wind and rainfall patterns that affect billions of people across South Asia, West Africa, East Asia, and other regions. As the subtropical highs move, they alter the flow of moisture-laden winds, steering them onto continents that were dry during other seasons. The result is a profound seasonal change, transforming landscapes from parched to waterlogged, bringing the rains that agriculture depends upon and shaping the rhythms of life across vast regions of our planet. The monsoons are not anomalies or exceptions. They are a natural consequence of the shifting patterns of atmospheric circulation that occur as our planet makes its yearly journey around the Sun. Weather doesn't exist in isolation. It emerges from differences, from contrasts and imbalances that nature constantly works to resolve. Differences in air pressure from one place to another, differences in temperature between neighboring regions, differences in how much moisture the air holds, these are the fundamental ingredients that generate everything we call weather. Where pressure is high in one location and low in another, air begins to move, creating wind. Where one air mass is warm and another cold, they eventually meet and interact, spawning storms along their boundary. Where moisture is abundant in one region and scarce in another, precipitation patterns emerge that can sustain rainforests or create deserts. The atmosphere is always responding to these differences, always trying to smooth them out, to redistribute heat and moisture more evenly, and yet the differences persist because the Sun keeps creating them, day after day. Weather is the atmosphere's endless, never quite successful attempt to achieve equilibrium on a planet that refuses to sit still. Understanding how air behaves as it moves vertically through the atmosphere is absolutely essential to understanding weather. When a parcel of air rises, something remarkable happens to it. As it climbs higher into the atmosphere, it encounters progressively lower pressure because there's less air weighing down from above. With lower pressure surrounding it, the air parcel expands, spreading out like a balloon inflating. But this expansion requires energy, and that energy comes from the heat within the air parcel itself. The molecules do work pushing outward against the lower pressure, and in doing so, they lose kinetic energy, which means they move more slowly, which means the temperature drops. This cooling happens automatically, inevitably, whenever air rises. It's not because the air is moving into a colder environment, though that may also be true. It's because the very act of rising and expanding causes the air to cool itself from within. This cooling of rising air follows a predictable pattern that meteorologists have measured and studied for more than a century. On average, if you could follow a parcel of air as it rose through the atmosphere, you'd find that its temperature decreases by about 6.5 degrees Celsius for every kilometer of altitude it gains. This is called the environmental lapse rate, and it represents the typical temperature structure of the atmosphere. It's not a law that air must follow, it's more like an average description of what the atmosphere usually looks like. The actual lapse rate varies from place to place and time to time depending on weather conditions, but this 6.5 degree drop per kilometer gives you a useful baseline for understanding why mountaintops are cold and why pilots need to worry about icing even on summer days when they climb high enough. But there's another lapse rate that's more fundamental, more tied to the physics of how air itself behaves. If you take a parcel of completely dry air and lift it upward, it will cool at a very specific rate determined by thermodynamics. This dry adiabatic lapse rate is about 9.8 degrees Celsius per kilometer, noticeably steeper than the average environmental lapse rate. The word adiabatic means that no heat is exchanged with the surrounding air, the cooling happens entirely because of expansion. This rate is remarkably consistent because it depends only on fundamental properties of air that don't change. Dry air rising in the morning cools at the same rate as dry air rising in the evening, over the ocean or over the desert, in summer or winter. It's one of the reliable constants in the chaos of weather. However, air is rarely completely dry. The atmosphere contains water vapor, that invisible gas that makes humidity, and when air containing moisture rises and cools, something important happens. Eventually, the air cools enough that it can no longer hold all its water vapor. The vapor begins to condense into tiny liquid droplets, forming a cloud. This condensation releases energy, a substantial amount of energy called latent heat. This is the same energy that was absorbed from the environment when the water originally evaporated, and now it's being given back. This release of heat warms the rising air from within, partially offsetting the cooling that would otherwise occur from expansion. As a result, moist air that's actively forming clouds cools more slowly than dry air as it rises. The moist adiabatic lapse rate is variable, depending on temperature and how much water vapor is condensing, but it's typically somewhere between 4 and 7 degrees Celsius per kilometer, significantly less than the dry rate. This difference between how dry air and moist air cool as they rise has profound consequences for weather. The latent heat released during condensation is not a trivial detail, it's a major energy source that can dramatically intensify weather systems. In thunderstorms, this released heat powers the strong updrafts that can reach speeds exceeding 100 miles per hour. The rising air keeps condensing moisture, which keeps releasing heat, which keeps the air warmer and more buoyant than its surroundings, which keeps it rising even faster. This feedback process can build towering cumulonimbus clouds that reach the stratosphere, clouds so energetic they generate lightning, hail, and sometimes tornadoes. The water cycle and the weather system are intimately connected through this exchange of latent heat. Every time water changes phase, from vapor to liquid or from liquid to ice, energy moves with it, and that energy can fuel the most powerful storms on Earth. The atmosphere has stable layers and unstable layers, times when air wants to rise and times when it resists rising. Conditional instability describes a particularly interesting situation. Imagine a layer of air near the surface that's relatively cool and stable early in the morning. As the sun rises and heats the ground, the lowest layer of air warms up. If this surface air warms enough, it can become buoyant compared to the air above it. Once it breaks through the stable layer overhead, it may find itself in an environment where it can rise freely, accelerating upward and potentially forming deep clouds and storms. The instability was conditional. It depended on the surface air being heated enough to overcome the stable layer that was initially capping it. This mechanism explains why thunderstorms often develop in the afternoon on summer days. The morning is calm and clear, but as the day heats up, the surface air finally becomes warm enough and moist enough to punch through the stable air aloft, and suddenly towers of clouds build where none existed an hour before. Meteorologists have developed ways to measure and quantify the potential for storms to develop. One of the most important measures is something called CAPE, which stands for Convective Available Potential Energy. CAPE measures the amount of energy available to a rising parcel of air once it becomes buoyant and begins accelerating upward. You can think of it as the fuel available for a storm. Higher CAPE values mean more energy is available, which generally means storms can become more intense, with stronger updrafts and more severe weather. On days when CAPE values are very high, perhaps several thousand joules per kilogram, meteorologists know that if storms do manage to form, they could quickly become powerful and dangerous. CAPE doesn't tell you whether storms will form, it tells you how strong they could become if they do form. It's a measure of potential, of the instability waiting to be released if the right trigger comes along. But potential instability isn't the whole story. Sometimes there's a lid on that potential, a layer of resistance that prevents storms from getting started in the first place. This resistance is quantified as CIN, or convective inhibition. CIN represents the amount of energy that would be required to lift a parcel of air from the surface up through stable layers to the point where it becomes buoyant and can rise on its own. You can think of CIN as a barrier, a hill that air must be pushed over before it can start rolling downhill and gathering speed. On days with high CIN, the atmosphere may have tremendous potential energy available aloft, but storms remain suppressed because surface air simply can't break through the stable layers. Weather forecasters pay close attention to the balance between CAPE and CIN. Strong CAPE with low CIN suggests explosive storm development is possible. Strong CAPE with high CIN suggests a frustrating day where storms struggle to form despite the instability overhead, unless something like a cold front comes along to force the air upward and overcome the inhibition. All of these processes, all of this rising and sinking and cooling and warming, depend fundamentally on one ingredient that makes up a surprisingly small fraction of the atmosphere. Water vapor constitutes only about 1 to 4% of the atmosphere's volume, depending on location and weather conditions. Compared to nitrogen at 78% and oxygen at 21%, water vapor is almost negligible in quantity. And yet this minor constituent fuels most of the energy that drives weather. Water vapor is the atmosphere's primary mechanism for storing and transporting energy. When water evaporates from the ocean or a lake, it absorbs a large amount of heat from its surroundings, cooling the surface but storing that energy in the vapor. The vapor can then be carried thousands of miles by winds, transporting that stored energy across continents and oceans. When the vapor finally condenses back into liquid, forming clouds and precipitation, all that stored energy is released back into the atmosphere, potentially powering storms far from where the water originally evaporated. Without water vapor, Earth's weather would be vastly simpler and far less energetic. There would still be winds driven by temperature differences, but the dramatic storms, the hurricanes and thunderstorms and blizzards that release such tremendous energy, these all depend on the latent heat contained in water vapor. This invisible gas, present in such small proportions, is what makes our weather truly dynamic and alive. The process of cloud formation is one of the most visible and beautiful expressions of atmospheric physics at work. It begins with warmth, with air that has been heated by contact with the sun-warmed ground or ocean surface. This warm air, being less dense than the cooler air around it, begins to rise, buoying upward like a hot air balloon lifting off the ground. As it rises, the air expands and cools, following those principles of expansion and temperature change that govern all rising air. The rising continues, the cooling continues, and eventually something magical happens. The temperature drops low enough that the air can no longer hold all of its water vapor in invisible gaseous form. The vapor begins to condense, transforming from gas into countless tiny liquid droplets, each one so small that it floats in the air rather than falling. These droplets scatter sunlight, making them visible as white or gray masses against the blue sky. A cloud is born, not from nothing, but from invisible moisture that was there all along, waiting for the right conditions to reveal itself. The formation of a cloud depends on air reaching a state called saturation, the point where the air holds as much water vapor as it possibly can at its current temperature. There are essentially two ways this can happen. The first and most common way is cooling. As air cools, its capacity to hold water vapor decreases. The same amount of moisture that was easily held by warm air becomes too much for cooler air to contain, and the excess condenses out. This is why clouds typically form as air rises and cools, why your breath becomes visible on cold mornings, why dew forms on grass overnight as temperatures drop. The second way to reach saturation is to add more moisture to the air without changing its temperature. This happens when water evaporates from a warm lake into cool air above it, creating fog, or when you take a hot shower and the bathroom fills with steam. In both cases, through cooling or moistening, the air reaches that critical threshold where vapor must become liquid. The temperature at which saturation occurs has a special name that every weather enthusiast knows. The dew point is the temperature to which air must be cooled for saturation to occur, assuming pressure and moisture content remain constant. The dew point is an absolute measure of how much moisture the air contains. High dew points mean the air is holding a lot of water vapor. Low dew points mean the air is relatively dry. On a summer day when the dew point is 70 degrees Fahrenheit or higher, you can feel the heaviness in the air, that sticky, humid sensation that comes from abundant moisture. On a crisp autumn day when the dew point has dropped to 40 degrees, the air feels dry and comfortable even if the temperature is still relatively warm. The dew point doesn't change as quickly or easily as temperature. It can only increase if moisture is added or decrease if moisture is removed. This stability makes dew point a reliable indicator of air mass characteristics. When the actual air temperature and the dew point are close together, clouds and fog are likely because only a small amount of cooling will bring the air to saturation. People often talk about humidity, but what they usually mean is relative humidity, which is a somewhat tricky concept. Relative humidity is the ratio of how much water vapor the air currently holds compared to the maximum amount it could hold at that temperature, expressed as a percentage. If relative humidity is 50%, the air is holding half the moisture it could theoretically hold. If it's 100%, the air is saturated and cannot hold any more. Here's the tricky part though. Relative humidity changes when temperature changes, even if the actual amount of moisture in the air doesn't change at all. Warm air can hold much more water vapor than cold air. So if you have air at 70 degrees with a certain amount of moisture giving you 50% relative humidity, and then the temperature drops to 50 degrees overnight without any moisture being added or removed, the relative humidity will climb, perhaps to 80 or 90%, simply because the cooler air's capacity has decreased. This is why relative humidity is usually lowest in the afternoon when temperatures peak and highest just before dawn when temperatures bottom out, even though the actual moisture content has barely changed. The atmosphere organizes itself into regions of high and low pressure, and these pressure systems have profound effects on the weather we experience. High-pressure systems, or anticyclones, are generally associated with pleasant weather, with clear skies and light winds. This happens because high pressure involves air that is sinking, descending from higher altitudes toward the surface. As this air sinks, it compresses under increasing pressure, and compression warms it. This warming moves the air further from saturation. Any clouds that might have existed evaporate, moisture capacity increases, and the sky clears. The sinking motion also prevents new clouds from forming because air that's sinking isn't rising, and cloud formation requires upward motion. People often welcome the arrival of high pressure because it means a break from storms, a chance for sunshine and stable conditions. The clear skies under high pressure can also lead to large daily temperature swings, with hot afternoons and cool nights, because without clouds to trap heat, radiation escapes freely into space after sunset. Low-pressure systems tell a completely different story. These are regions where air is converging at the surface, flowing together from surrounding areas. This converging air has nowhere to go but up. It rises, and as it rises, it cools, and as it cools, moisture condenses, forming clouds and often precipitation. Low-pressure systems are the storm makers, the weather producers. They bring the overcast skies, the rain, the snow, the unsettled conditions that can last for days as a low-pressure system slowly moves through a region. The rising air in a low creates a kind of suction effect at the surface, drawing air inward from all directions. This is why winds spiral into low-pressure centers, why storms develop circulation patterns. The stronger the low pressure, the more vigorous the rising motion, and generally the more intense the weather associated with it. Anticyclones have a characteristic structure that's important for understanding how they affect weather. At the surface, winds spiral outward from the high-pressure center. This diverging air must be replaced, which is why air sinks from above in a high-pressure system. The sinking air completes the circulation, descending from altitude, warming as it descends, and then spreading outward at the surface. Above the surface, free from the complicating effects of friction with the ground, the circulation is cleaner and more organized. The Coriolis effect causes the outflowing air to curve, creating a clockwise rotation around high-pressure centers in the northern hemisphere and counterclockwise in the southern hemisphere. These rotating high-pressure systems can be vast, sometimes spanning 1,000 miles or more, and they can persist for days or even weeks, dominating weather patterns over large regions. Weather maps display atmospheric pressure using lines called isobars, a term that comes from Greek words meaning equal pressure. Each isobar connects all the points where the atmospheric pressure is the same, much like contour lines on a topographic map connect points of equal elevation. By looking at how isobars are arranged on a map, you can learn a great deal about what the wind is doing and what weather to expect. Where isobars are packed tightly together, close to one another, the pressure is changing rapidly over distance. This means a strong pressure gradient exists, and strong pressure gradients produce strong winds. Where isobars are widely spaced, pressures change gradually, and winds are typically light. Meteorologists can estimate wind speed just by measuring the spacing between isobars. The patterns isobars make also reveal the locations of high and low pressure centers, fronts, and other important weather features. Reading a weather map covered in isobars is like reading the atmosphere's blueprint, seeing the invisible architecture of pressure that shapes the visible weather. High above the surface, typically above about 3,000 feet, the wind behaves in a particularly elegant way. Here, friction with the Earth's surface becomes negligible, and the wind responds primarily to just two forces: the pressure gradient force pushing air from high to low pressure, and the Coriolis effect deflecting moving air. These two forces balance each other, creating what meteorologists call geostrophic wind. Geostrophic wind flows parallel to the isobars rather than across them, neither toward high pressure nor toward low pressure, but right along the pressure contours. In the northern hemisphere, if you stand with your back to the geostrophic wind, low pressure will be to your left and high pressure to your right. This is called Buys-Ballott's law, named after the Dutch meteorologist who described this relationship in the 19th century. The geostrophic wind represents a kind of equilibrium, a balance between forces that allows air to flow smoothly around pressure systems rather than directly into or out of them. But near the surface, where we live and experience weather directly, friction complicates everything. The ground, with its forests and cities and fields and rough terrain, drags on the moving air, slowing it down. This friction reduces wind speed, sometimes by as much as half compared to the wind speed at higher altitudes. But friction does something else that's equally important. By slowing the wind, friction reduces the Coriolis effect, which depends on wind speed. With a weakened Coriolis effect, the pressure gradient force becomes relatively stronger, and instead of balancing perfectly, the wind veers away from its geostrophic direction. It turns toward the low pressure, crossing the isobars at an angle instead of flowing parallel to them. This is why surface winds spiral inward toward low pressure centers and outward from high pressure centers, rather than simply circling around them. The angle at which winds cross the isobars depends on how rough the surface is. Over the smooth ocean, the angle might be only 10 or 15 degrees. Over rough land with buildings and forests, it might be 30 or 40 degrees. This turning of the wind toward low pressure is crucial because it creates the convergence that forces air to rise in low pressure systems, which leads to clouds and precipitation, which creates the weather that makes low pressure systems matter in the first place. Without friction, weather would be different, more symmetric perhaps, but also missing some of the complexity that makes it so endlessly fascinating. The atmosphere isn't uniform. It doesn't have the same properties everywhere at once. Instead, it organizes itself into vast bodies of air, each with distinct characteristics of temperature and moisture that remain relatively consistent across hundreds or even thousands of miles. These bodies of air are called air masses, and they form when air sits over a uniform surface for an extended period, days or weeks, absorbing the characteristics of the region below. Over a cold ocean in winter, air becomes cool and moist, taking on the properties of the water beneath it. Over a vast desert or frozen tundra, air becomes dry, its moisture content dropping as it spends time over a surface that offers little water to evaporate. Over tropical seas, air becomes warm and humid, loading itself with moisture from the endless expanse of warm water. These air masses, once formed, can travel great distances, carried by the global wind patterns, bringing their characteristics to regions far from where they originated. When an air mass from the Arctic plunges southward into the United States, it brings biting cold and clear skies. When tropical air surges northward, it brings warmth and humidity that can feel oppressive to those unaccustomed to it. Air masses that form over oceans, called maritime air masses, have one defining characteristic that shapes all their behavior. They are moist. The ocean surface constantly evaporates water into the air above it, and over days and weeks, the air becomes laden with water vapor. This moisture makes maritime air masses the cloud makers, the rain bringers. When maritime air is forced to rise, whether by flowing over mountains or by colliding with other air masses, that abundant moisture readily condenses, forming extensive cloud systems and often producing precipitation. Maritime tropical air masses, forming over warm tropical oceans, are particularly rich in moisture and can generate heavy rainfall when they move over land. Maritime polar air masses, forming over cold northern or southern oceans, carry less moisture than their tropical cousins but still contain enough water vapor to produce clouds and showers, especially when the air is forced upward. Coastal regions often experience weather dominated by maritime air masses, with frequent clouds, moderate temperatures, and regular precipitation throughout the year. In contrast, continental air masses form over the vast interiors of continents, far from any significant body of water. These air masses have a defining dryness because land surfaces, especially in winter or in arid regions, provide little moisture for evaporation. Air sitting over the interior of Siberia in winter or the Sahara in summer becomes profoundly dry, its relative humidity dropping to values that can make the air feel almost brittle. Continental air masses resist cloud formation because they simply lack the moisture needed to reach saturation when they rise. When continental air dominates a region, skies tend to be clear or only partly cloudy, precipitation becomes rare, and daily temperature ranges can be extreme because the lack of clouds and moisture allows temperatures to swing widely between day and night. Continental air masses can bring beautiful clear weather, but they can also bring drought when they persist too long over agricultural regions. Temperature provides another crucial way to classify air masses, and polar air masses represent the cold end of this spectrum. These form at high latitudes, in regions where the sun angle is low and heating is weak. The air becomes cold, often bitterly so in winter, and it also becomes stable. Cold air is dense, heavy, and it tends to sink rather than rise. This stability means that polar air masses resist the kind of vertical motion that would produce clouds and storms. When a polar air mass moves into a region, it typically brings cold temperatures and clear skies, though if the cold air moves over a warmer surface like an unfrozen lake or ocean, the heating from below can destabilize the lowest layers, producing scattered clouds and even snow showers. Continental polar air is especially dry and cold, forming over places like northern Canada or Siberia, and when it surges equatorward, it can bring record-breaking cold to regions hundreds of miles to the south. Maritime polar air is less extreme, moderated by its oceanic origin, but still brings cool temperatures and often cloudiness to the regions it affects. On the opposite end of the temperature spectrum are tropical air masses, born in the low latitudes where solar heating is intense year-round. These air masses are warm by definition, and they serve a crucial role in the global climate system by transporting heat away from the tropics toward the poles. Tropical air masses are the atmosphere's way of sharing warmth, of moderating the temperature difference between equator and poles that would otherwise be even more extreme. Maritime tropical air masses, forming over warm tropical oceans like the Gulf of Mexico or the tropical Atlantic, are both warm and moist, creating a combination that can produce impressive weather when conditions are right. When this air is lifted, either by frontal systems or by flowing over terrain, it can generate heavy thunderstorms and copious rainfall. Continental tropical air masses are less common but do form over subtropical deserts in summer, bringing hot, dry conditions when they move into neighboring regions. The heat waves that bake the southwestern United States in summer often result from continental tropical air masses that have formed over the deserts of Mexico or the American Southwest. The most interesting weather, the most dramatic weather, often occurs not in the heart of an air mass but at its boundaries, where different air masses meet. These boundaries are called fronts, and they're zones of contrast, places where temperature and moisture change rapidly over a short distance. The word front comes from military terminology, borrowed during World War I when Norwegian meteorologists developed the conceptual framework for understanding these boundaries. A front is essentially a battlefield where air masses collide, and like any battlefield, it's a place of conflict and action. Warm air and cold air don't mix easily. They have different densities, different properties, and when they meet, one must override the other. The cold air, being denser, tends to wedge underneath the warm air like a plow blade, forcing the warm air to rise. This rising motion, this forced ascent of warm air, is what produces the clouds and precipitation associated with fronts. Warm fronts occur when warm air is advancing, moving into a region previously occupied by cold air. The warm air can't simply push the cold air out of the way because the cold air is heavier and hugs the ground. Instead, the warm air rides up and over the cold air in a long, gradual slope. This slope is gentle, perhaps only 1 kilometer of rise for every 100 or 200 kilometers of horizontal distance. Because the slope is so gentle, the lifting of warm air occurs slowly and over a broad area. This produces widespread cloudiness that can extend hundreds of miles ahead of where the front is marked at the surface. The clouds typically arrive in a sequence, high thin cirrus clouds first, appearing perhaps a day before the front arrives, then gradually lowering and thickening to altostratus, then to stratus, and finally to nimbostratus as the front approaches, bringing steady, persistent precipitation. Warm fronts rarely produce severe weather, but they can produce impressive rainfall totals because the precipitation, though not intense, can continue for many hours as the front slowly passes. After a warm front passes, temperatures rise, humidity increases, and the air feels distinctly different, softer and heavier than before. Cold fronts present a much different character. These occur when cold air is advancing, plowing into a region occupied by warm air. The cold air moves like a wedge, steep and aggressive, undercutting the warm air and forcing it to rise rapidly. The slope of a cold front is much steeper than that of a warm front, perhaps 1 kilometer of rise for every 50 to 100 kilometers of horizontal distance. This steep slope means the lifting is concentrated in a relatively narrow band, and it's rapid and vigorous. The warm air doesn't rise gently, it's shoved upward forcefully, and this can trigger intense convection. Cold fronts are associated with lines of thunderstorms, sometimes severe, that march along the frontal boundary. The precipitation from a cold front is often heavy but brief, a burst of intense rain or hail that moves through quickly as the front passes. Behind a cold front, temperatures drop, sometimes dramatically, humidity decreases, and winds often shift abruptly, typically to a direction with north in its name. The sky clears rapidly after the front passes, and the air feels crisp and fresh, cleaned by the passage of the storm. Sometimes the dance between warm and cold fronts becomes more complex. Cold fronts typically move faster than warm fronts because the dense cold air can wedge forward more efficiently. When a cold front catches up to a warm front ahead of it, something called an occluded front forms. The cold air behind the cold front collides with the cool air ahead of the warm front, and the warm air that was between them gets lifted entirely off the ground, squeezed upward between two masses of colder air. Occluded fronts can be quite complex in their structure and behavior, and they often mark the mature or decaying stage of a mid-latitude cyclone. The weather associated with occluded fronts varies depending on the specific temperature contrasts involved, but generally includes extensive cloudiness and precipitation. Occluded fronts indicate that a storm system is evolving, that the simple pattern of warm and cold fronts is giving way to something more intricate as the system ages. Not all fronts move. Sometimes the forces pushing warm air and cold air against each other reach a stalemate, a balance where neither air mass can advance. This creates a stationary front, a boundary that sits in roughly the same location for days, oscillating back and forth perhaps, but not making any significant progress in either direction. Stationary fronts can be frustrating for anyone hoping for a change in weather because they mean the weather pattern has become stuck. If you're on the cool side of the front, you may experience day after day of clouds and drizzle. If you're on the warm side, the weather might be more pleasant, but still cloudy as moisture streams northward along the front. Eventually, something breaks the stalemate. A change in the upper atmosphere winds, the development of a new low-pressure system, some shift in the larger weather pattern finally gets the front moving again. It may begin advancing as a warm front or a cold front, ending the period of stagnation and bringing changes to the regions that have been trapped in the same weather for so long. Fronts, in all their varieties, are where weather happens, where the atmosphere's drama unfolds, where calm gives way to storms and one air mass surrenders to another in the endless cycle of atmospheric change. High above the everyday weather, typically around the altitude where jet aircraft cruise, rivers of air race across the planet at speeds that can exceed 200 miles per hour. These are the jet streams, narrow bands of exceptionally fast wind that circle the globe in the upper troposphere and lower stratosphere. The jet streams aren't part of the weather in the way that rain or wind at the surface is part of weather, but they're profoundly important because they steer weather systems, guiding storms along their paths like currents guide ships at sea. The position and strength of the jet stream determine where storms will develop and which regions will experience active weather versus calm conditions. A dip in the jet stream can funnel cold Arctic air southward, bringing unseasonable cold to regions far from the poles. A northward bulge in the jet stream can allow warm air to surge to unusually high latitudes, creating record warmth in places that are typically cool. Meteorologists pay constant attention to the jet stream because it's the key to understanding where weather will develop and how it will evolve over the coming days. The jet streams don't flow in perfect circles around the planet. Instead, they meander, undulating north and south in great waves that can span thousands of miles. These waves are called Rossby waves, named after Carl Gustav Rossby, a Swedish-American meteorologist who explained their physics in the 1930s and 40s. Rossby waves form because of the way the Coriolis effect changes with latitude, combined with the conservation of a property called potential vorticity. The mathematics is complex, but the result is visible on any upper-level weather map. The jet stream snakes across the hemisphere in a series of ridges where it bows northward and troughs where it dips southward. These waves don't just sit in place, they can propagate around the globe, and they can also amplify or decay depending on conditions. When a Rossby wave pattern becomes established and persists, it can lock weather patterns in place for weeks at a time. A persistent ridge can bring prolonged warm, dry weather to the region beneath it, potentially leading to drought and heat waves. A persistent trough can subject a region to week after week of cool, stormy conditions. The pattern becomes stuck, and the weather becomes repetitive, day after day of similar conditions that can be either delightful or frustrating depending on what those conditions happen to be. Sometimes the jet stream develops a particularly strong ridge, a northward bulge of high pressure that becomes so robust and stationary that it blocks the normal west-to-east progression of weather systems. These blocking highs are atmospheric roadblocks, forcing storm systems to divert around them like traffic detouring around construction. A blocking high over the eastern Pacific can keep storms away from California, contributing to drought. A block over the North Atlantic can redirect storms either far to the north or far to the south, dramatically affecting weather across Europe. Blocking patterns are notoriously persistent. Once established, they can last for weeks, and during that time, weather patterns become highly predictable in a local sense but highly unusual from a climatological perspective. The regions under the block experience prolonged fair weather, often with temperatures warmer than normal because the sinking air in the high-pressure system warms by compression. Meanwhile, regions forced to sit on the stormy side of the block endure persistent, unsettled weather. Blocking patterns eventually break down, but predicting exactly when this will happen remains one of the more challenging aspects of medium-range weather forecasting. Much closer to the ground, within the lowest kilometer of the atmosphere, a different kind of mixing and turbulence dominates. This region is called the planetary boundary layer, and it's where the atmosphere directly feels the effects of the Earth's surface. During the day, the sun heats the ground, and the ground heats the air in contact with it. This creates instability, with warm air rising and cooler air sinking, generating turbulent eddies that churn the boundary layer like water boiling in a pot. This turbulence is crucial because it mixes heat, moisture, and momentum throughout the boundary layer. Heat from the surface gets distributed upward rather than remaining trapped at ground level. Moisture evaporated from the surface gets carried aloft. Faster winds from higher altitudes get mixed downward. Without this turbulent mixing, the lowest layer of air would become extremely hot and stagnant during the day, and weather would be very different from what we actually experience. The boundary layer turbulence is invisible most of the time, but you can sometimes see its effects in the dancing of dust devils, the fluttering of leaves, or the bumpy ride experienced by aircraft flying at low altitude on a hot afternoon. Mountains create their own wind systems, local circulations that develop in response to the uneven heating and cooling of sloped terrain. During the day, when the sun shines on a mountain slope, that sloped surface heats up, and it heats the air in contact with it. This air becomes warmer than the air at the same altitude over the adjacent valley, and being warmer, it becomes buoyant and rises along the slope. This creates a valley breeze, a gentle wind that flows upslope during daytime hours, carrying air from the valley floor toward the peaks. Hikers and climbers often notice this wind on sunny afternoons, a soft breeze blowing uphill, sometimes bringing puffy cumulus clouds that form over the peaks as the rising air cools and its moisture condenses. The valley breeze is usually strongest in the afternoon when heating is most intense, and it plays an important role in the mountain environment, helping to ventilate valleys and influence where clouds and precipitation form. At night, the process reverses. Mountain slopes radiate heat to space and cool rapidly, much more rapidly than the air at the same altitude hanging over the valley. The air in contact with the cooled slope becomes cold and dense, and like any dense fluid, it wants to sink. It drains downslope, flowing like an invisible river of cold air down the mountainside and pooling in the valley below. This is called a mountain breeze, though it's sometimes also called a katabatic wind or drainage wind. Mountain breezes can be surprisingly strong and persistent, and they create the phenomenon of temperature inversions in mountain valleys, where the coldest air sits at the bottom while warmer air resides at higher elevations on the slopes. This is why frost occurs first in valley bottoms and why smoke from a campfire in a valley can get trapped and linger rather than dispersing. Orchardists and vintners pay close attention to these drainage winds, sometimes planting their sensitive crops on slopes rather than valley floors to avoid the coldest air. The difference in how land and water respond to heating creates some of the most familiar local wind patterns. Land has a low heat capacity. It heats up quickly when the sun shines on it and cools quickly when the sun sets. Water, by contrast, has an enormous heat capacity. It takes a great deal of energy to change its temperature, and it holds on to that heat for a long time. This difference drives sea breezes along coastlines. During the day, the land heats rapidly while the ocean temperature barely changes. The air over the hot land rises, creating lower pressure at the surface. The cooler, denser air over the ocean flows inland to replace the rising air, creating a sea breeze. Anyone who has spent time at the beach on a hot day knows the relief that arrives when the sea breeze kicks in, that cool, moist wind flowing from the water that can drop temperatures by 10 or 15 degrees in the space of an hour. At night, the land cools rapidly while the ocean remains relatively warm. The pressure pattern reverses, and a weaker land breeze blows from land towards sea, though this nocturnal breeze is usually less noticeable than its daytime counterpart. The ocean's enormous heat capacity has implications far beyond daily sea breezes. Oceans absorb solar energy throughout the summer, storing vast amounts of heat in their upper layers. They release this heat slowly throughout the fall and winter, warming the air above them. This creates moderate climates along coasts, where winters are milder and summers are cooler than in continental interiors at the same latitude. Seattle and Minneapolis sit at nearly the same latitude, but Seattle's proximity to the Pacific Ocean gives it far milder winters despite being farther north in some seasons. The ocean acts as a thermal buffer, resisting temperature changes and creating climatic stability. This moderating influence extends inland wherever winds blow from the ocean toward land, but it's strongest right along the coast where the contrast between land and water is most direct. Islands and narrow peninsulas surrounded by water have especially moderate climates, never getting as cold in winter or as hot in summer as continental locations. The wind doesn't just affect the atmosphere, it also sets the ocean in motion, creating currents that flow through the sea. But ocean currents don't flow in the same direction as the wind that drives them, at least not exactly. This is because of something called the Ekman spiral, named after Van Wolfried Ekman, a Swedish oceanographer who worked out the physics in the early 1900s. When wind blows across the ocean surface, it drags the surface water along, but the Coriolis effect deflects this moving water to the right in the northern hemisphere. The surface water then drags the water below it, which is also deflected by the Coriolis effect, and this continues down through the water column. Each layer moves a bit slower and is deflected a bit more to the right than the layer above it, creating a spiral pattern of currents that decrease in speed and rotate in direction with depth. The net result, averaged through the depth of wind influence, is that water transport occurs roughly 90 degrees to the right of the wind direction in the northern hemisphere, 90 degrees to the left in the southern hemisphere. This might seem like an obscure detail, but it has profound consequences for ocean circulation and coastal phenomena. These wind-driven currents, along with currents driven by differences in water temperature and salinity, form a global system of ocean circulation that redistributes heat across the planet. Warm water flows from the tropics toward the poles, carrying heat poleward and helping to moderate polar climates. Cold water flows from the poles toward the equator, cooling tropical and subtropical regions that would otherwise be even warmer. The Gulf Stream carries warm water from the Gulf of Mexico across the Atlantic toward Europe, and this warmth, released to the atmosphere as the water crosses the ocean, helps keep Western Europe far warmer than other regions at the same latitude. Without the Gulf Stream, London would have a climate more like that of Labrador, which sits at the same latitude but lacks the warming influence of a warm ocean current. The ocean currents work in tandem with atmospheric circulation to transport heat around the globe, and together these systems maintain a climate that's far more moderate and habitable than it would be if heat remained where the sun deposited it. The ocean and atmosphere are partners in the dance of weather and climate, each influencing the other in ways that create the conditions we experience every day. Thunderstorms are among the most dramatic and powerful expressions of atmospheric energy, and they arise from a deceptively simple recipe. Take warm, moist air near the surface, place it in an environment where the atmosphere above is unstable, and provide some trigger to start the air rising. Once the process begins, it can become almost explosive. The warm air accelerates upward, condensing its moisture into towering clouds that can reach 10 or even 15 kilometers high. Inside these clouds, powerful updrafts and downdrafts battle each other, rain and hail form and fall, lightning flashes through the electrically charged interior, and thunder rumbles across the landscape. Thunderstorms are heat engines, converting the latent heat stored in water vapor into kinetic energy, into the violent motions of air and the dramatic weather that makes these storms both beautiful and dangerous. They form over tropical oceans and continental interiors, over mountains and plains, anywhere the conditions align to allow deep convection to develop. The scale of thunderstorm activity on Earth is almost incomprehensible. At any given moment, roughly 2,000 thunderstorms are in progress somewhere on the planet. That's not 2,000 per day or 2,000 per hour. That's 2,000 at once, every minute of every day, year-round. The atmosphere is continuously generating these storms, an endless parade of convection that spans the globe. Some are small and brief, lasting only 20 or 30 minutes and affecting only a few square miles. Others are massive complexes that persist for hours and spread across multiple states or countries. Together, these storms dump millions of tons of rain, generate countless lightning strikes, and release energy equivalent to many nuclear weapons every single day. And yet, despite this enormous scale of activity, each individual thunderstorm follows the same basic life cycle, from birth through maturity to dissipation, governed by the same physical principles. A thunderstorm reaches its mature stage when both updrafts and downdrafts coexist within the same storm cell. In the early stages, when the storm is just forming, it's all updraft, all rising motion carrying warm moist air upward. But as precipitation forms in the upper parts of the cloud, that precipitation eventually becomes heavy enough to fall. The falling rain drags air downward with it, creating a downdraft. When this downdraft reaches the surface, it spreads outward, bringing a rush of cool air that marks the arrival of the storm. This is the mature stage, when the storm is at its most intense, when rain is heaviest, when lightning is most frequent, when hail may fall and winds may gust to damaging levels. The updraft continues to feed the storm with energy from below, while the downdraft evacuates used air and precipitation. This balance can persist for 30 minutes or longer in a well-organized storm, creating a steady roar of thunder and a drumming of rain that can be both exhilarating and frightening to experience. One of the most distinctive features of a mature thunderstorm is its anvil-shaped top, a flat spreading canopy that extends outward from the main body of the storm. This anvil forms because the rising air in the thunderstorm eventually encounters a barrier it cannot penetrate. The troposphere, where weather occurs, extends up to a boundary called the tropopause, beyond which lies the stratosphere. The stratosphere is stable, with temperatures that increase with altitude rather than decrease, and this stability acts like a lid on the atmosphere. When the powerful updraft in a thunderstorm hits this lid, it can't rise any further. The air spreads outward instead, flowing horizontally in all directions, carrying ice crystals with it. These ice crystals, spread across tens or even hundreds of miles, form the anvil cloud, a warning that can be seen from great distances that a powerful thunderstorm is at work. The anvil typically points in the direction the upper-level winds are blowing, stretched downwind by the jet stream or other high-altitude winds, creating that characteristic shape that gives this cloud feature its name. The downdrafts in thunderstorms don't form simply from the weight of falling precipitation, though that's part of the story. There's a more subtle process at work involving evaporative cooling. As rain falls from the cloud into drier air below, some of that rain evaporates. Evaporation requires energy, heat energy, which is taken from the surrounding air. This cools the air, making it denser and heavier. This cooled air sinks, accelerating downward and creating a downdraft that's stronger than what the weight of the precipitation alone would produce. In the most intense thunderstorms, these downdrafts can become remarkably powerful, creating what meteorologists call a microburst when the downdraft hits the ground and spreads outward violently. These microbursts are particularly dangerous because they occur on a small scale, typically less than 2.5 miles across, but they can produce winds exceeding 150 feet per second, strong enough to snap trees, destroy buildings, and pose extreme hazards to aircraft. Hail is one of the more remarkable products of thunderstorms, solid ice falling from the sky on a summer afternoon when ground-level temperatures may be well above freezing. Hail forms through a process of repeated cycling through different temperature zones within a thunderstorm. A raindrop gets caught in a strong updraft and is carried high into the cloud where temperatures are well below freezing. The drop freezes into ice. But instead of falling immediately, the strong updraft carries it back up through regions of supercooled water, liquid droplets that haven't frozen despite being colder than the freezing point. These supercooled drops freeze onto the hailstone, adding a layer of ice. Eventually, the hailstone becomes too heavy for the updraft to support, and it begins to fall, but then it encounters another strong updraft and gets recycled back up into the freezing zone. Each cycle adds another layer of ice. If you cut open a large hailstone, you can see these layers like rings in a tree, each one representing a trip through the storm. The largest hailstones, some approaching the size of softballs, have made dozens of trips through the storm before finally falling to the ground. Only the strongest thunderstorms, those with the most powerful updrafts can produce large hail, because only they can support the weight of growing ice long enough for it to reach impressive size. Among all thunderstorm phenomena, tornadoes inspire perhaps the most awe and fear. These violently rotating columns of air descend from certain thunderstorms and can produce the strongest winds observed anywhere on Earth. Tornadoes don't form from just any thunderstorm. They require a special breed of storm called a supercell, a long-lived rotating thunderstorm with a persistent updraft that can tilt and organize rotation extending through a deep layer of the atmosphere. The rotation in a supercell comes from wind shear, changes in wind speed and direction with height that create horizontal rotation in the air. The thunderstorm's updraft tilts this horizontal rotation into the vertical, creating a rotating updraft called a mesocyclone. Under certain conditions, this rotation can tighten and intensify, stretching downward from the cloud base. If it reaches the ground and produces damage, it's classified as a tornado. The exact process by which tornadoes form is still not completely understood despite decades of research. It's a problem of small-scale dynamics occurring within a larger storm, influenced by subtle details of wind, temperature, and moisture that can vary dramatically over short distances and brief time periods. Water can produce its own versions of rotating columns, though generally less intense than tornadoes. Waterspouts develop over warm water, often in tropical or subtropical regions, when atmospheric conditions favor the development of rotating columns but don't necessarily involve the powerful supercell structure that produces the strongest tornadoes. Fairweather waterspouts, the most common variety, form when warm water heats the air above it, creating instability and rising motion. If rotation is present, perhaps from converging sea breezes or local wind patterns, this rotation can tighten as air rises, much like a figure skater spins faster when pulling in their arms. The result is a slender, often graceful-looking funnel that extends from a small cumulus cloud down to the water surface, where it raises a spray ring as it sucks water upward. Waterspouts can persist for 10 or 20 minutes before dissipating, and while they're generally weaker than tornadoes, they can still be dangerous to boats and coastal structures if they move on shore. Not all rotating atmospheric phenomena require thunderstorms or even clouds. On hot, sunny days with light winds, the intense heating of the ground can create localized areas of extreme instability. If a pocket of very hot air breaks free and begins to rise, conservation of angular momentum can cause it to spin, especially if there's any initial rotation in the air from local winds flowing around obstacles. This creates a dust devil, a rotating column of rising air made visible by the dust and debris it lofts from the ground. Dust devils are usually small, perhaps 10 to 100 feet in diameter, and brief, lasting only a few minutes. But they can occasionally become quite intense, with winds strong enough to cause minor damage or injuries. They're most common in desert regions where the ground gets extremely hot, but they can occur anywhere when conditions are right. Unlike tornadoes, dust devils form from the ground up rather than descending from clouds, and they don't require storms or precipitation. They're creatures of sunshine and heat, dry weather phenomena that demonstrate how the atmosphere can organize rotation even in the absence of clouds or rain. The birth of tropical storms begins in a region of the ocean where the water temperature crosses a critical threshold. When sea surface temperatures reach about 28 degrees Celsius, roughly 82 degrees Fahrenheit, the ocean holds enough heat energy to potentially spawn tropical cyclones. This warm water is the fuel tank for these storms, providing the energy that will eventually power winds exceeding 100 miles per hour and waves that can reshape coastlines. The process starts modestly, with a cluster of thunderstorms forming over the warm ocean. If atmospheric conditions are favorable, this cluster can organize itself into a tropical depression, a loosely defined area of low pressure with winds beginning to circulate around a center. At this early stage, the system is barely recognizable as what it might become. Winds are light, perhaps 20 to 30 miles per hour, and the circulation is often ragged and disorganized. But given the right conditions, this humble beginning can evolve into one of nature's most powerful storms. One of the key ingredients for tropical storm development is something that might seem counterintuitive at first. These storms need calm conditions aloft, specifically low wind shear. Wind shear, the change in wind speed or direction with altitude, can tear a developing tropical system apart, tilting its circulation and preventing the vertical organization that's essential for intensification. Strong wind shear disrupts the symmetry of the storm, pushing the upper-level clouds away from the lower-level circulation, cutting off the feedback processes that allow the storm to strengthen. When wind shear is low, however, the storm can build vertically like a perfectly stacked tower. Rising air can ascend through the entire depth of the troposphere without being pushed sideways. Heat released by condensation warms the core of the storm, lowering pressure at the center, which draws in more air at the surface, which rises and releases more heat, creating a self-reinforcing cycle. The storm intensifies, sometimes with shocking rapidity, going from a disorganized cluster of thunderstorms to a dangerous hurricane in less than 24 hours when conditions are optimal. The warm ocean is not just a passive participant in this process. It actively fuels the hurricane through a continuous exchange of heat and moisture. At the ocean surface beneath the storm, water evaporates into the air, loading it with water vapor. This moist air spirals inward toward the center of the storm and then rises vigorously in the towering thunderstorms that make up the hurricane structure. As this air rises and the water vapor condenses, latent heat is released, enormous amounts of it, and this heat warms the air and maintains the buoyancy that keeps it rising. The rising air flows outward at high altitude, completing a circulation pattern. At the surface, more air rushes in to replace what has risen, and this inward rush is what we experience as the hurricane's winds. The warmer the ocean, the more water vapor can evaporate, and the more energy is available to power the storm. This is why hurricanes weaken when they move over cooler water or land. They're cut off from their energy source, like unplugging an electric motor. In the northern hemisphere, hurricanes spin counterclockwise, a consequence of the Coriolis effect acting on the converging winds. As air flows toward the low-pressure center, it's deflected to the right, creating a counterclockwise rotation when viewed from above. This rotation is essential to the hurricane's structure and intensity. The spinning motion helps organize the storm, concentrating the strongest winds in a ring around the calm center, the eye of the hurricane. Inside the eye, winds are light. The sky may even be clear or partly cloudy, creating an eerie calm that contrasts sharply with the violence just outside. The eye wall surrounding this calm center is where the hurricane's strongest winds occur, where rising air is most intense, where the storm's fury reaches its peak. The counterclockwise circulation also determines which side of the storm is most dangerous. In the northern hemisphere, the right side of a northward moving hurricane, relative to its direction of motion, experiences the strongest winds because the storm's rotational wind and its forward motion add together on that side. While tropical cyclones dominate attention in summer and fall, a different breed of storm governs weather in the mid-latitudes during the cooler months. Mid-latitude cyclones, also called extratropical cyclones, form along the boundaries between warm and cold air masses in the zones where fronts collide and interact. These storms don't have the symmetric structure of hurricanes. Instead, they're lopsided, asymmetric systems with warm air on one side and cold air on the other, with the strongest winds often concentrated in a narrow zone along the cold front. Mid-latitude cyclones develop through a process called baroclinic instability, which converts the potential energy stored in horizontal temperature contrasts into the kinetic energy of winds and storms. A disturbance in the jet stream, a ripple in the upper-level flow, can trigger the development of a surface low-pressure system. As the low intensifies, it draws in warm air from the south and cold air from the north, wrapping these air masses around itself in a characteristic spiral pattern that's visible on satellite images. Winter storms in the mid-latitudes can achieve impressive intensity, sometimes producing blizzard conditions, coastal flooding, and widespread power outages. These storms intensify through many of the same principles that govern all low-pressure systems, but with the added energy that comes from strong temperature contrasts available in winter. When very cold continental air collides with warm, moist air from the ocean, the stage is set for explosive development. The warm air is forced to rise along the cold front, and as it rises, moisture condenses, releasing latent heat. This heat release warms the mid-levels of the storm, strengthening the pressure gradient and accelerating winds. The strongest winter storms often develop when a surface low-pressure system moves along the coast where warm ocean water can provide abundant moisture, while cold air plunging southward from Canada provides the temperature contrast. The interaction of these ingredients can produce storms that rival hurricanes in wind speed and far exceed them in size, with storm systems spanning thousands of miles and affecting multiple states or provinces simultaneously. The atmosphere has developed a particularly efficient mechanism for transporting water vapor across ocean basins. Atmospheric rivers are long, narrow corridors of concentrated moisture, typically only a few hundred miles wide but thousands of miles long, that flow through the atmosphere like rivers of vapor coursing through the sky. These features form when weather patterns organize to create a persistent flow of air from tropical or subtropical regions toward the poles, and if this flow passes over warm ocean waters, it picks up enormous amounts of moisture along the way. A single atmospheric river can transport more water vapor than the Mississippi River transports in liquid form. When an atmospheric river makes landfall and is forced to rise over coastal mountains, the resulting precipitation can be staggering, with rainfall totals exceeding 10 or even 20 inches in a single event. The west coast of North America is frequently affected by atmospheric rivers that originate over the Pacific and slam into California, Oregon, or Washington, bringing flooding rains and mountain snows. These events are crucial for water resources, providing much of the annual precipitation these regions receive, but they can also be destructive when they're particularly intense or prolonged. Every few years, the tropical Pacific Ocean and atmosphere engage in a remarkable dance that affects weather worldwide. El Niño is a disruption of the normal patterns in the tropical Pacific, characterized by unusually warm water spreading across the central and eastern Pacific Ocean. During normal conditions, trade winds blow from east to west across the tropical Pacific, piling warm water up in the western Pacific near Indonesia and allowing cooler water to upwell along the coast of South America. During El Nino, these trade winds weaken or even reverse. The warm water sloshes back eastward, and the entire pattern of where air rises and sinks across the Pacific shifts. This shift has cascading effects around the globe. Heavy rainfall that normally falls over Indonesia and Australia shifts eastward, bringing drought to those regions while causing flooding in the Central Pacific and along the west coast of South America. The jet stream over North America shifts position, altering storm tracks and affecting weather from California to Florida. El Nino events demonstrate how interconnected Earth's climate system is, how changes in one region can propagate around the world through atmospheric and oceanic connections. The atmospheric circulation that El Nino disrupts is called the Walker circulation, named after Sir Gilbert Walker, a British scientist who described this pattern in the early 20th century. Under normal conditions, air rises over the warm waters of the western tropical Pacific, where Indonesia and northern Australia are located. This rising air creates clouds and heavy rainfall, making these among the wettest regions on Earth. The rising air flows eastward at high altitude, sinks over the cooler eastern Pacific near South America, and flows back westward at low altitude as the trade winds, completing the circulation loop. This pattern is remarkably persistent under normal conditions, maintaining the characteristic climate zones of the tropical Pacific. During El Nino, the Walker circulation weakens or even reverses as the warm water and rising air shift eastward. During La Nina, the opposite of El Nino, the Walker circulation intensifies, with stronger trade winds and an even more pronounced east-west contrast in Pacific temperatures and rainfall. These fluctuations in the Walker circulation are part of a natural oscillation that has been occurring for thousands of years, long before humans were around to observe and name it. Cold air has a weight and presence that warm air lacks. Near the poles, especially during winter darkness, the ground radiates heat to space and becomes bitterly cold. The air in contact with this frozen surface becomes cold and dense, heavy as liquid, pooling over the polar regions in massive high-pressure systems. These polar highs can contain air so cold that breathing it feels like inhaling razors, air at temperatures 40 or 50 degrees below zero, sometimes even colder. This air doesn't stay confined to the poles. Periodically, when the atmospheric circulation pattern is right, some of this frigid air breaks free and surges equatorward, pushing into mid-latitude regions that are unprepared for such cold. These Arctic outbreaks or polar vortex events can bring record-breaking cold to regions thousands of miles from the Arctic, plunging temperatures in Texas or Florida to levels more typical of Canada, freezing crops, straining power systems, and creating dangerous conditions for anyone caught unprepared. The cold air is often accompanied by clear skies and light winds within the high-pressure system itself, but at its leading edge, where it collides with warmer air, storms can develop, mixing snow and ice with the advancing cold. These outbreaks are a reminder that weather knows no fixed boundaries, that air formed over the Arctic ice can, within a few days, find itself bringing winter to regions that barely recognize the season. Fog is essentially a cloud that has formed at ground level, and like all clouds, it appears when air reaches saturation and water vapor condenses into tiny droplets suspended in the air. The process requires cooling, a reduction in temperature that brings the air to its dew point. When this cooling happens near the surface rather than aloft, fog forms instead of clouds floating overhead. Walking through fog is an intimate experience with the atmosphere's water cycle, moving through a mass of suspended droplets so small they fall imperceptibly slowly, creating that characteristic dampness that settles on your skin and clothes. Visibility drops, sometimes to just a few feet, as light scatters off millions upon millions of these tiny droplets. The world becomes muffled and mysterious, sounds dampened, distances impossible to judge. Fog transforms familiar landscapes into strange and sometimes beautiful places, softening hard edges and hiding details beyond a certain distance. On clear, calm nights with light winds, a particular type of fog often develops through a process that begins with the ground itself. After sunset, the ground radiates heat to space, and without clouds to trap this heat and send it back down, the surface cools rapidly. The air in direct contact with the cooling ground also cools, and if there's sufficient moisture present, this cooling can bring the air to saturation. Fog forms first in the lowest layer, perhaps just a few feet thick, and then deepens as the night progresses and cooling continues. This is radiation fog, named for the radiative cooling process that creates it. By dawn, valleys and low-lying areas can be filled with dense fog, pools of white that make travel hazardous and delay the start of morning activities. Radiation fog is most common in autumn when nights are long and cool but moisture is still abundant from summer. As the sun rises and begins heating the ground, the fog usually dissipates, burning off as warming air can hold more moisture and droplets evaporate. By mid-morning, the fog that seemed so thick and persistent earlier has vanished, leaving only dampness on grass and leaves as evidence it was ever there. Another common fog type forms through horizontal movement of air rather than radiative cooling. Advection fog develops when warm, moist air moves across a cooler surface, whether that surface is cold ocean water, snow-covered ground, or just land that has been cooled by a previous cold spell. The classic example occurs along coastlines where warm air from over the ocean moves inland at night and encounters ground that has cooled after sunset. The air's lower layers cool on contact with the cold surface, reaching saturation and forming fog. Advection fog can be particularly persistent because it doesn't require clear skies or calm winds like radiation fog does. In fact, the wind is what brings the warm air over the cold surface in the first place. Coastal areas like San Francisco experience advection fog for much of the summer, created when warm Pacific air flows over the cold California current and then moves inland through gaps in the coastal mountains. This fog can last all day, refusing to burn off, creating the characteristic cool, grey summers that define that region's climate. Mountains are sculptors of weather, obstacles that force air to respond to their presence. When a moving air mass encounters a mountain range, it has no choice but to rise. This forced ascent is called orographic lift, and it's one of the most reliable mechanisms for producing clouds and precipitation. As the air rises up the windward slope of the mountain, it expands and cools, and if it was carrying moisture, that moisture eventually condenses into clouds. If the air is moist enough and the mountain tall enough, these clouds will produce precipitation, often copious amounts. The windward sides of mountain ranges are typically lush and green, watered by orographic rainfall that can exceed 100 inches per year in extreme cases. Meanwhile, the lee side of the mountain, the side away from the prevailing winds, sits in what's called a rain shadow. The air descending down the lee slope warms and dries, having already wrung out most of its moisture on the windward side, and the result is a much drier climate. The contrast can be dramatic. The western slopes of the Cascade Range in Washington and Oregon are temperate rainforests, while just 50 miles to the east, the land is semi-arid shrub steppe. In tropical regions, a different rainfall mechanism dominates. Here, intense solar heating creates powerful convection, with hot air rising vigorously throughout the afternoon. This convectional rainfall doesn't require fronts or mountains. It's driven purely by surface heating creating instability. Every afternoon in the tropics, you can often see towering cumulus clouds building as the day heats up, and by mid-afternoon, thunderstorms erupt, dumping heavy rain for an hour or two before dissipating as the sun sets and heating weakens. This daily cycle of heating and rainfall is remarkably consistent in many tropical locations, creating a rhythm to the day that locals plan around. Morning is often clear, afternoon brings storms, evening returns to calm. Annual rainfall totals from this convectional process can be enormous, supporting the tropical rainforests that depend on this abundant and reliable moisture. The storms are typically brief but intense, with rainfall rates that would be considered extreme in mid-latitude regions but are routine in the tropics. Sometimes precipitation forms high in a cloud but never reaches the ground. Virga is the name for these streaks of rain or snow that fall from a cloud base but evaporate or sublimate in the dry air below before touching the surface. From a distance, virga appears as gray or dark streaks hanging beneath a cloud, curtains of precipitation that fade to nothing in mid-air. It's especially common in arid regions where the air near the surface is very dry. The precipitation falling through this dry air evaporates, taking heat from the air and cooling it in the process. Sometimes this cooling can create downdrafts that reach the ground as gusty winds even though no rain does. Virga can be frustrating in drought-stricken areas, tantalizing evidence of moisture aloft that provides no relief to the parched ground below. But it's also strangely beautiful, visible proof of the atmosphere's complexity, of precipitation that begins but doesn't complete its journey. Winter precipitation comes in many forms, and one of the more interesting is graupel, sometimes called soft hail or snow pellets. Graupel forms when snowflakes fall through a layer of supercooled water droplets, tiny drops of liquid water that remain unfrozen despite being colder than the freezing point. When a snowflake collides with these droplets, they freeze onto its surface instantly, coating the delicate ice crystal with a layer of rime. As this process continues, the snowflake becomes encased in frozen droplets, losing its intricate structure and becoming a small, opaque pellet of ice. Graupel bounces when it hits the ground, unlike snow which simply accumulates, and it makes a distinctive sound when falling on surfaces, a soft rattling quite different from the silence of falling snow. Graupel is common in winter thunderstorms and in conditions where temperatures are near freezing. It's less dense than true hail but harder than snow, occupying a middle ground in the spectrum of frozen precipitation. In extremely cold conditions, usually well below freezing, a rare and eerie type of fog can form through a process that bypasses the liquid phase entirely. Sublimation fog, also called ice fog, occurs when water vapor sublimates directly into ice crystals in very cold air. This typically happens when moisture is suddenly introduced into bitterly cold air, such as when open water exists in subarctic regions, or when vehicle exhaust adds moisture to frigid air in northern cities. The water vapor doesn't condense into liquid droplets first. The air is too cold for that. Instead, it transforms directly from gas to solid, forming tiny ice crystals that hang in the air, glittering in sunlight. Ice fog can be incredibly persistent in Arctic regions, lingering for days in calm, cold conditions. The ice crystals are so small they stay suspended almost indefinitely, creating visibility as poor as any liquid fog but with the added hazard of coating surfaces with frost and making breathing difficult in the extreme cold. All rain is slightly acidic, even rain falling through pristine air far from any pollution. This natural acidity comes from carbon dioxide dissolving in water droplets as they form and fall. Carbon dioxide reacts with water to form carbonic acid, the same weak acid that makes carbonated beverages tingly on your tongue. This gives clean rain a pH of about 5.6, slightly acidic on the pH scale where 7 is neutral. This natural acidity is generally harmless and is actually important for weathering rocks and cycling nutrients through ecosystems. Of course, rain can become much more acidic when it falls through air containing pollutants like sulfur dioxide or nitrogen oxides, which form stronger acids. But even in a world without pollution, rain would still be slightly acidic because of atmospheric carbon dioxide, a reminder that what we sometimes think of as pollution is often an exaggeration of natural processes. Raindrops themselves are fascinating objects, far more complex than the teardrop shapes often drawn in cartoons. Small raindrops are nearly spherical, held into that shape by surface tension. As they grow larger, they become more flattened on the bottom by air resistance, taking on a shape more like a hamburger bun. The largest raindrops, those approaching the size of a housefly or about 5 or 6 millimeters in diameter, are the biggest that can exist in stable form. Anything larger becomes unstable and breaks apart into smaller drops. These large drops fall at speeds approaching 30 kilometers per hour, though smaller drops fall much more slowly, sometimes drifting down at just a few kilometers per hour. The size of raindrops affects how rain feels when it hits you, how it sounds on a roof, how effectively it soaks into soil versus running off. Tropical downpours often feature large drops falling fast, creating that distinctive heavy feel of tropical rain. Drizzle consists of tiny drops falling slowly, barely more than a mist. The simple act of rain falling encompasses a remarkable range of drop sizes and fall speeds, all part of the endless complexity of weather. Weather, in all its complexity and variety, can be broken down into 6 fundamental elements that define atmospheric conditions at any given moment. Temperature tells us how hot or cold the air is, a measure of the kinetic energy of air molecules. Pressure indicates the weight of the atmosphere pressing down from above, revealing where air is rising or sinking. Wind describes air in motion, flowing from high pressure toward low pressure, bent by Earth's rotation and slowed by friction. Humidity quantifies the moisture content of air, the invisible water vapor that fuels clouds and precipitation. Clouds themselves are visible collections of water droplets or ice crystals suspended in the air, indicators of atmospheric processes at work. And precipitation is water falling from the sky in liquid or frozen form, the atmosphere's way of redistributing moisture from where it evaporates to where it falls. These 6 elements interact constantly, each influencing the others in ways that create the endless variety of weather we experience. A change in temperature affects how much moisture air can hold. Changes in pressure create winds. Winds transport moisture. Moisture forms clouds. Clouds affect temperature by blocking sunlight or trapping heat. The elements are threads in a fabric, woven together so tightly that you cannot pull on one without affecting all the others. The atmosphere is extraordinarily sensitive to small changes, a characteristic that makes weather both fascinating and frustrating. A tiny difference in temperature or humidity in one location can grow over time, amplifying through the atmospheric system until it produces dramatically different weather days or weeks later. This happens because weather is a chaotic system in the mathematical sense, not chaotic meaning random or disordered, but chaotic meaning that small differences in initial conditions lead to large differences in outcomes. 2 weather scenarios that start out nearly identical can diverge rapidly, becoming completely different within a week or two. This sensitivity places fundamental limits on how far into the future we can predict weather with any accuracy. Even if we could measure the atmosphere perfectly, which we cannot, and even if our computer models were perfect representations of atmospheric physics, which they are not, we would still run into this inherent unpredictability after a certain point. The atmosphere simply doesn't allow for perfect long-range prediction because of its chaotic nature. This sensitivity to initial conditions has been famously described as the butterfly effect, a term that comes from a metaphorical question posed by meteorologist Edward Lorenz in the 1970s. Could a butterfly flapping its wings in Brazil eventually cause a tornado in Texas? The question isn't meant to be taken literally. It's pointing to the idea that tiny disturbances, things too small to measure or even notice, can theoretically grow over time to influence large-scale weather events. A butterfly's wings don't actually cause tornadoes, of course, but the metaphor captures something profound about atmospheric dynamics. The atmosphere is so sensitively balanced, so intricately connected across scales from millimeters to thousands of kilometers, that we can never know its state well enough to predict its evolution indefinitely. This is why weather forecasts are quite good for the next day or two, reasonably good for 3 to 5 days, become increasingly uncertain beyond a week, and are essentially guesswork beyond 2 weeks. It's not because meteorologists aren't skilled or computers aren't powerful enough. It's because the atmosphere itself resists long-range prediction through its fundamental nature. To make any forecast at all, meteorologists must first observe the current state of the atmosphere across multiple scales. The microscale includes phenomena smaller than a kilometer, things like individual thunderstorms or the turbulent eddies in the boundary layer. The mesoscale encompasses weather features from a few kilometers to a few hundred kilometers, including thunderstorm complexes, sea breezes, and small frontal systems. The synoptic scale covers the continent-spanning weather systems we see on television weather maps, the highs and lows and fronts that determine general weather patterns. And the global scale includes phenomena like the jet stream, El Niño, and the general circulation patterns that wrap around the entire planet. Each scale influences the others, smaller features adding up to create larger patterns, while larger patterns provide the environment in which smaller features develop. Understanding and predicting weather requires observing all these scales simultaneously, a monumental task that requires a vast global observing system. The foundation of weather observation is the surface weather station, thousands of which dot the globe, measuring temperature, pressure, humidity, wind speed and direction, and precipitation. These stations provide ground truth, actual measurements of conditions at Earth's surface, the level where we experience weather most directly. The data they collect flows into meteorological centers around the world every hour, forming the raw material that feeds weather prediction models. Over land, weather stations are relatively dense in developed countries but sparse in remote regions. Over the oceans, which cover most of Earth's surface, stations are limited to islands and ships, leaving vast areas with minimal direct observation. This uneven distribution of observations creates uncertainty in our knowledge of current conditions, uncertainty that can grow into forecast errors as predictions extend into the future. To understand the atmosphere, we need to know not just what's happening at the surface but throughout its entire vertical extent. Twice daily, at coordinated times around the world, weather services launch radio SANs, instrument packages attached to weather balloons that rise through the atmosphere while transmitting measurements back to ground stations. As the balloon ascends, it measures temperature, humidity, pressure, and wind at various altitudes, creating a vertical profile of atmospheric conditions from the surface up to heights of 20 or 30 kilometers before the balloon bursts. These soundings reveal the structure of the atmosphere in ways surface observations cannot, showing where stable layers exist, where moisture is concentrated, how winds change with height. This information is crucial for understanding whether thunderstorms will develop, how strong storms might become, where precipitation will occur. The twice-daily launch schedule, at midnight and noon Greenwich Mean Time, creates a synchronized global snapshot of atmospheric structure that has been maintained for decades, providing consistency and continuity in observations. Satellites orbiting overhead provide a perspective on whether that was impossible before the space age. From hundreds of miles above Earth, satellites capture images of clouds, track their movement and evolution, measure temperatures at various levels in the atmosphere, and even detect moisture and winds. Geostationary satellites hang over one spot on the equator, rotating with Earth and providing continuous coverage of the same region, capturing images every few minutes that can be assembled into time-lapse sequences showing weather systems develop and move. Polar orbiting satellites circle Earth from pole to pole, providing higher resolution but less frequent coverage of any particular location. Together, these satellites create a comprehensive view of global weather, revealing patterns and systems that would be invisible from the ground. The swirl of a hurricane, the march of frontal systems across an ocean, the intricate texture of cloud patterns, all become visible from space in ways that transform our understanding of weather. For very short-term predictions, particularly warnings of severe weather, meteorologists rely heavily on radar. Weather radar sends out pulses of radio waves that bounce off precipitation particles and return to the radar antenna. By analyzing these return signals, radar can detect rain, snow, or hail, determine how intense it is, and track its movement. Modern Doppler radar can also detect motion toward or away from the radar, revealing wind patterns within storms and identifying rotation that might indicate tornado formation. Radar provides information on a scale of minutes and kilometers, allowing meteorologists to issue warnings with lead times of tens of minutes for phenomena like tornadoes or flash floods. This nowcasting, predicting what will happen in the next hour or two based on current radar trends, has saved countless lives by giving people time to take shelter before dangerous weather arrives. Radar data updates every few minutes, providing a near real-time view of precipitation that complements the broader, less detailed picture from satellites. All these observations, from surface stations and radiosondes and satellites and radar, flow into powerful computer systems that run atmospheric models, mathematical representations of how the atmosphere works. These models divide the atmosphere into a three-dimensional grid, calculating conditions at millions of points around the globe. They simulate the physics of air motion, heat transfer, moisture processes, and radiation, advancing the state of this virtual atmosphere forward in time step by step. Each time step might represent a few minutes of real time, and the model runs forward for days or weeks, creating a prediction of how weather will evolve. These simulations are running constantly, multiple times per day, ingesting the latest observations and producing updated forecasts. The models create virtual Earths inside computers, digital twins of our atmosphere that evolve according to the laws of physics, providing a glimpse into possible futures. The forecasts you see on television or your phone are derived from these model simulations, interpreted and refined by meteorologists who understand the model's strengths and weaknesses and can add human judgment to the raw computer output. Weather prediction has become a partnership between human expertise and computational power, combining observations, physics, and experience to peer as far into the future as the atmosphere's chaotic nature will allow. At the heart of modern weather forecasting lies numerical weather prediction, a process that treats the atmosphere as a physical system governed by mathematical equations. These equations describe how air moves, how heat flows, how moisture transforms between phases, how pressure changes, all the fundamental processes that create weather. The equations themselves have been known for more than a century, derived from basic physics principles like conservation of mass, energy, and momentum. But solving these equations for the entire atmosphere, with all its complexity and interaction across scales, requires immense computational power. Supercomputers work through trillions of calculations, solving the equations at millions of grid points scattered throughout a three-dimensional representation of the atmosphere, advancing the solution forward in tiny time steps that accumulate into forecasts days ahead. These machines run continuously, processing new observations as they arrive and generating updated predictions multiple times each day. The supercomputers used for weather prediction are among the most powerful on Earth, their processing capacity dedicated to the single task of simulating atmospheric behavior with enough accuracy and detail to provide useful guidance about future weather. No forecast is perfect, and meteorologists have developed ways to quantify the uncertainty inherent in their predictions. Ensemble forecasting runs not just one simulation but many, perhaps 20 or 50 or even more, each starting from slightly different initial conditions or using slightly different model physics. These variations represent the uncertainty in our observations and our understanding of atmospheric processes. As the ensemble members run forward in time, they begin to diverge, exploring different possible futures. If all the ensemble members agree closely, forecasters can be confident in the prediction. If the members spread widely, showing many different possible outcomes, confidence is low and forecasters know that unusual or unexpected weather might occur. Ensemble forecasts provide a range of possibilities rather than a single prediction, acknowledging that the atmosphere's chaotic nature prevents us from knowing the future with certainty. This probabilistic approach has revolutionized forecasting, allowing meteorologists to communicate not just what they think will happen but how confident they are in that prediction. The atmosphere doesn't sit still while models run. Conditions change continuously as weather evolves, and observations stream in from around the world every hour. Data assimilation is the sophisticated process of incorporating these new observations into running models, adjusting the model's representation of the atmosphere to match reality as closely as possible. This isn't as simple as just replacing model values with observed values, because observations are scattered unevenly in space and time, while models need complete three-dimensional fields. Data assimilation uses mathematical techniques to optimally blend observations with model predictions, weighing each piece of information according to its reliability and relevance. The result is an analysis, a best estimate of current atmospheric conditions that combines the strengths of observations and models. This analysis then becomes the starting point for the next forecast. Data assimilation runs continuously in a cycle, observations improving the model filling gaps between observations, creating a feedback loop that keeps weather predictions anchored to reality even as they project into an uncertain future. Early weather models couldn't resolve individual thunderstorms or other small-scale features because their grid spacing was too coarse, often hundreds of kilometers between grid points. These models had to parameterize convection, using simplified mathematical representations to estimate the collective effects of thunderstorms without actually simulating them. Modern high-resolution models use much finer grid spacing, sometimes just a kilometer or even less between grid points. At these resolutions, the models can explicitly simulate convection, actually forming virtual thunderstorms in their digital atmospheres. This allows the models to capture details like individual storm cells, squall lines, and the complex interactions between storms and their environment. High-resolution models are computationally expensive, requiring even more powerful supercomputers and producing enormous amounts of data, but they provide forecasts of detail and accuracy that were impossible just a decade or two ago. They can predict not just that thunderstorms will occur, but approximately where individual storms will form and how intense they might become. Machine learning and artificial intelligence are beginning to play larger roles in weather prediction, though not replacing traditional physics-based models but rather complementing them. Machine learning algorithms excel at pattern recognition, finding subtle relationships in vast datasets that might elude human observers or traditional statistical methods. These algorithms can be trained on decades of weather observations and forecasts, learning to recognize patterns associated with particular weather outcomes. They can help identify situations where models typically perform poorly, adjust forecasts based on known biases, or provide rapid predictions that supplement slower physics-based models. Machine learning is particularly useful for nowcasting, making very short-term predictions based on current observations, and for post-processing model output to correct systematic errors. The combination of physics-based understanding and data-driven pattern recognition promises to push weather forecasting toward even greater accuracy, though fundamental limits imposed by atmospheric chaos will always remain. In the atmosphere, not all winds behave in the balanced, smooth manner of geostrophic flow. Ageostrophic winds are the departures from this balance, the components of wind that don't follow isobars but instead cross them, flowing toward lower pressure or away from higher pressure. These ageostrophic components may be small compared to the total wind, but they're crucial because they drive convergence and divergence, the coming together or spreading apart of air that forces vertical motion. In developing storms, ageostrophic winds create the convergence at low levels that forces air upward, initiating and maintaining the convection that powers the storm. Understanding and predicting these subtle ageostrophic components is essential for forecasting where and when storms will intensify. They represent the imbalance in the atmosphere, the deviation from equilibrium that allows weather to change and evolve rather than settling into static patterns. The atmosphere is filled with waves, not sound waves or light waves, but waves of air density and pressure that propagate through the fluid atmosphere. These atmospheric waves transport momentum and energy across vast distances, redistributing these quantities from where they're generated to where they're absorbed or dissipated. Gravity waves, generated by thunderstorms or flow over mountains, can carry energy vertically and horizontally, affecting weather far from their source. Rossby waves, those great meanders in the jet stream, transport momentum and heat across hemispheres. When these waves break or dissipate, they deposit their momentum, affecting the circulation in ways that can alter weather patterns. The global redistribution of energy and momentum by waves is part of how the atmosphere maintains its general circulation, how it transports excess heat from the tropics toward the poles, how it prevents temperature differences from growing even larger than they already are. Mountains create more than just orographic lift and rain shadows. When strong winds blow across a mountain range, they can generate topographic waves, oscillations in the airflow that extend far downstream of the mountain. These waves can extend high into the atmosphere, reaching the jet stream level, and they can influence the path and speed of the jet stream itself. A major mountain range like the Rockies or the Himalayas acts as a permanent disturbance to atmospheric flow, continuously generating waves that affect weather patterns hundreds or thousands of miles downwind. These topographic waves contribute to the development of surface weather systems, can enhance or suppress storm formation, and play a role in determining where ridges and troughs in the jet stream preferentially form. The solid Earth beneath the atmosphere shapes weather in ways that persist long after air has moved far from the mountains that disturbed it. The boundary between the troposphere and stratosphere isn't impermeable. Material can cross from one layer to the other, and one important substance that makes this journey is ozone. The stratosphere contains most of Earth's ozone, formed by the action of ultraviolet light on oxygen molecules. Sometimes stratospheric air intrudes downward into the troposphere, bringing ozone-rich air into the lower atmosphere where it affects chemistry and can impact air quality. These intrusions often occur near jet streams and in the vicinity of strong weather systems where vertical motions can reach high into the atmosphere. Ozone transported from the stratosphere is chemically different from tropospheric ozone, and tracking these stratospheric intrusions helps scientists understand both air quality near the surface and the exchange processes between atmospheric layers. The atmosphere isn't neatly divided into separate, isolated layers, but rather exchanges material between levels through complex processes that operate continuously. The climate is changing, warming in response to increasing greenhouse gas concentrations, and this warming is affecting weather in ways both subtle and dramatic. A warmer atmosphere can hold more water vapor, roughly 7% more for each degree Celsius of warming, following basic thermodynamic principles. This means more moisture is available for storms, allowing them to produce heavier rainfall when conditions are favorable. Warmer temperatures also mean more energy is available to fuel convection, potentially creating more intense thunderstorms and more severe weather. Heat waves become more frequent and more intense as the baseline temperature shifts upward, making what was once an extreme temperature now merely unusual, and creating new extremes that exceed anything in the historical record. Cold extremes become less frequent, though they still occur. The warming doesn't eliminate winter or cold weather, it shifts the odds, making some types of weather more likely and others less so. Weather has always been variable and extreme at times, but climate change is loading the dice, increasing the probability of certain high-impact weather events while decreasing others. Understanding weather in the 21st century requires understanding not just atmospheric physics but also how a warming climate is changing the environment in which weather occurs, altering the baseline from which extremes depart.